Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic and tells you more about admissible rules. So remember, a rule in a system of logic is something of the form, if these things are theorems, then this other thing is a theorem. And an admissible rule, or a rule, is admissible if every substitution instance of the if side, if those things are theorems, then every substitution instance of the then side is a theorem. And we've talked about how derivable rules are going to be admissible because it's quite easy. You do the derivation, you do the substitution instance, there you go. But I want to look at a rule today that is admissible in system K, but is not derivable. And it's not derivable for a very particularly interesting reason. It's also an interesting rule because it is admissible in system K. But we will see later on that if we have a stronger system, the rule that might have been admissible in K might not be later. So this is another place where admissible and derivable rules come apart, because derivations, once you have them, you've got them. So anytime any rule that is going to be admissible in a weak system of logic any rule that is derivable in a weak system of logic will continue to be derivable as you add more axioms and you strengthen the system, because making the system stronger never takes away things you've already proven. It only allows you to prove more things. This is actually the crux of the point for why some rules might be admissible in a weak system of logic, but not in a stronger system, because since you can now prove more things, the if part of your rule suddenly comes into play more. So let me bring up the board so that I can show you the rule that is admissible but not derivable in system K. So rule, this is admissible in K but not derivable. And it is the rule that if in system K you can prove something of the form possibly phi, then in system K, you can prove phi. So why is this admissible? It's admissible because whatever substitution instance of the antecedent, so possibly P, or possibly P or not P, or possibly whatever complex formula you want, if that thing is a theorem of K, then the corresponding substitution instance of the consequence of the rule, i.e. removing the box, will also be a theorem. This is because this will never be a theorem. So there are no theorems of K which have possibility as the main operator. This is because K is the system that characterizes what you can prove, what is valid in any Kripke frame whatsoever. Now, we will show later on kind of the close connection between validity and provability in kind of Kripke frames in general and system K in particular. But note that the single world that doesn't see anything, is a completely well-formed Kripke frame. We've also seen that anytime that you have a dead end, so if W is a dead end, then all formulas of the form necessarily phi are true, and all formulas of the form possibly phi are false. So this means that any formula whose main connective is a possibility can be falsified on a Kripke frame simply by finding a dead-end world. This therefore means that if we could prove something of the form possibly phi as a theorem in K, we would be proving something that could possibly be false. And that would mean that K is not sound. But we proved in earlier videos that it is sound. So because K is sound, we know that there will never be any theorem of the form possibly phi. And that's why this is an admissible rule. Because if I say, if something that will never happen happens, then something else is the case. But the antecedent is never going to happen because we will never have anything of the form as a theorem, possibly phi. We will see later systems where this isn't true, where we do have theorems that have possibility as the main connective. And in this case, in those systems, this isn't going to be an admissible rule, because just because something is possible doesn't mean that it is true at the actual world. We will, way down the line from now, see a system in which this rule becomes admissible again, even though there are theorems of the system that have possibility as the main connective. So there you have it, an example of a rule that is admissible in K, will become unadmissible in another stronger system, but will become admissible again in one of the strongest systems that we will look at. Hopefully this brief example gives you an idea of kind of how admissibility and derivability come apart. This is something where there's actually a whole bunch of really interesting sort of properties of logics that rely on admissible versus derivable rules, and when they coincide and when they come apart. I'll say something about this in the next video, just very briefly. But for what we do from now on, it isn't necessarily going to be terribly important. We're just going to be interested in the derivable rules, and I will give you more examples of them as we come to them to make your proofs easier. Until then, take care, enjoy your logic, and see you later. Cheers.